Hi, so I'm going to be talking about a very simple algorithm that's extremely useful in cases where you have very, very tall, skinny matrices that you know the columns are reasonably well conditioned. So there aren't a few columns that are almost exactly linear combinations of the other columns. So in these cases, we might want to perform an algorithm called a Cholesky-based QR decomposition. So it's really quite simple to motivate. The idea is that if we know that we'd eventually like the QR decomposition of A, we could write A equal QR, where again, Q is a unitary matrix and R is an upper triangular matrix. And what I want you to think of is the fact that A is very tall and skinny, so you might want to think of this decomposition as looking something like this, where each column of Q is very long and there are only a few of them, and they're all mutually orthonormal. Okay, and so then the matrix R would be very, very tiny, and it would be upper triangular. Okay, so if we then formed A adjoint A, then it should be clear that this would be equal to R adjoint Q R. Okay, but since the columns of Q are mutually orthonormal, this is then equal to R adjoint R. Okay, but again, R is upper triangular. So this is precisely a Cholesky factorization of A adjoint multiplied by A. So this implies an algorithm for computing the QR decomposition of A. So the first step would be to form, say, Z equal to A adjoint A, where conceptually you can think of that as producing a really small square symmetric matrix as the product of a long row vector, or the adjoint of very tall, skinny matrix with multiplied by itself. Okay, so we can actually perform this if A is m by n, where m is much, much larger than n, then this can be performed in n squared n floating point operations. So this would be n squared n flops. Okay, so then the next step would be that we would compute a Cholesky factorization of this really small matrix Z. In particular, we compute the upper Cholesky factorization. So I would say R is equal to Chol of Z. Okay, this is actually very cheap to compute since this matrix Z is very small. It's, you can think of maybe something like 100 by 100. The number of flops required here is actually going to be 1/3 n cubed. Again, n is much, much smaller than m. Think of m as, I don't know, 100 million, and n is maybe 10 or 100. Okay, so now we have R, and what we want is a QR decomposition of A. So naturally, we could say that Q is equal to A multiplied by the inverse of R. So then the third step of our algorithm would be Q is formed as A R inverse. Okay, well, again, R is an n by n triangular matrix, and the cost of performing a triangular solve against an n by n matrix is n squared flops. Now, there are m rows of A, therefore, the cost of performing m such triangular solves is m n squared, which is actually the same as the first step. Okay, so what I want you to recognize is that it's extremely easy to parallelize the first and the last step. In particular, suppose that we just used a one-dimensional decomposition of this very tall, skinny matrix A. So what I've drawn on the board is what we would do if we had 8 processes. So if the height of this matrix was 8 million, then process 0 would get the first million rows, process 1 would get the next million, etc. So the idea is that we could perform this first operation of multiplying A adjoint by A in the same manner, essentially, that we would perform something like a vector inner product. So if you recall from previous videos, when we performed, say, X adjoint multiplied by X, when X is a vector, all we had to do is perform a local portion of the inner product and then perform something like an MPI all reduce summation on the result. So we can do exactly the same thing here. So the way we would perform step 1 would be that we would have process I would form Z sub I updated with a sub I adjoint multiplied by a sub I. So in this case, the work required is m over p times n squared, where p is the number of processes. OK. And so then if we wanted to actually compute z from this, it's simply the summation of all the z sub i's. So the next step would be to perform MPI all reduce in order to compute z as the sum over all the processes of z sub I. OK, so I'll leave that to you to recall what the cost is for all reduce. So in the second step, since n is assumed to be very small, what we might want to do is just have every process redundantly compute this Cholesky factorization. So if n is very small, then this would essentially be an ignorable operation. Now the third step is actually now trivially parallel. So the reason is that we can actually rewrite this as saying for each block, say the ith block that we want to compute of Q is simply equal to a sub I multiplied by R inverse. And the reason is that what we're doing is we're performing triangular solves against each row of A in this operation. So each of those triangular solves is independent, so we can just give each process some chunk of those. And then the work that's performed here is now m over p times n squared. So the only thing that I haven't drawn on the board now is what the cost is of performing this MPI all reduce over the z sub i's, which were the contributions towards A adjoint A. But that's simply just a standard cost for performing, say, an MPI all reduce on an n by n chunk of data. So I'll leave that to you to fill in what the details are there. But what we see is that we have a very simple algorithm for performing something that's actually quite useful. And again, the caveat is that you should only use this in cases where, one, the matrix is very tall and skinny, and two, you know that the columns are reasonably well conditioned. Thanks.